In this section, we shall take up the elements of sampling distribution and after that chi-square distribution. Before going into the sampling distribution, we need to know some important properties or concepts. First, we will take up population. It is the totality of all individuals or objects belonging to a given field of inquiry. What do you mean by totality of all individuals or objects? Let us consider two examples. Suppose we consider the collection of all students in a college. Suppose we conduct some survey on the college students, and for a college we take all students. So this is the totality. Suppose we want to know the consumption pattern of average families. So as the population we can take up the collection of all commodities in a market. So these are the populations. But we have to remember one thing, that in any statistical study, it is not feasible or possible to enumerate the whole population. So we have to resort to a part of the population that is meant to represent the whole population is called a sample. If we recall the examples that we took in population, so what can be the sample? In the first example, when we took up the collection of all students in a college, as the sample we can take some students of this college, maybe a collection of students consisting of say 5 students from each stream. Similarly, when we are talking of consumption pattern, instead of considering all possible commodities in a market, we can think of a list of commodities that is used by an average family. So you see, these are basically the parts of the given population, but these are used to represent the whole population. So one problem comes in our mind, we have to remember this thing, that how to represent the population, that problem is to be addressed. So when we have to take a part of the population, as I mentioned, that we have to think how the part or the sample will represent the whole population will depend on how we draw the sample. This act of drawing the sample is called sampling. The selection or drawing of individuals or objects from a population in order is called sampling. This term, this phrase in order is very important because from the population we do not select some individuals together. We select the individuals one after another or one by one. So there always be the first member selected or the first unit selected, there will always be the second member selected or second unit selected and so on. So that means the selection has to be done in order. Now this sampling can be of two main types, subjective and objective. What do you mean by subjective sampling? The sampling rule depends upon the sampler. That is, the procedure in which I will take the sample, I will draw the sample will depend on me if I am the sampler. On the other hand, in case of objective sampling, the sampler does not have any role to play. Here the sampling rule is given from the outside and the sampler just follows the rule to get the sample. We take an example. Suppose there are 6 members in a population and we have to select 2 of them. That means my population size is 6 and the sample size is 2. Now, there are 2 ways of drawing this. Suppose I know 2 of these 6 members well, so I can select those 2 individuals. So can you tell me what kind of sampling will this be? Subjective or objective? Definitely subjective, because I am selecting the 2 members, because I know the 2 individuals well. Had there been some other person, he might have selected some other 2 individuals because he might have known those 2 other individuals better. On the other hand, what can be the objective sampling? It may be something like this. Suppose I have an unbiased die with me and I decide that I will select the first person if 1 comes while rolling a die. I'll select the second person if the die shows me number 2 and so on. So you see here the sampling rule does not depend on me. It doesn't depend on me whom I'll be selecting in my sample. The die will dictate, the throwing of the die, the point that will appear on the die, that will dictate whom to be selected. So here the sampling rule is given from the outside. Now can you tell me which is better, subjective sampling or objective sampling? there is no hard and fast rule to say whether subjective sampling is better or objective sampling is better. Actually, when I want my individuals to be selected according to my will, maybe in case of an index number, then we go for subjective sampling. But when we want the sampling rule to be given from outside and whoever is the sampler, he'll get the corresponding sample, then we will follow objective sampling. In our course of study, we shall consider objective sampling. And the most important of objective sampling is simple random sampling. It is a type of objective sampling where each member or unit of the population has an equal probability of being selected. So they have an equal probability of being selected. If we recall the example of objective sampling that we taken, that there are 6 individuals in the population and we will select 2 of them by throwing a die. Now you can imagine that when I'll get 1, I'll take the first individual. When I'll get 2, I'll take the second individual, and so on. Now see, what is the probability of getting 1? When we throw an unbiased die once, 1 by 6. So what is the probability of selecting the first individual from the population? 1 by 6. Probability of selecting second individual population? That is also 1 by 6. Probability of selecting the third individual? 1 by 6. So everybody 1 by 6. So there is an equal probability of being selected in the sample. So it is simple random sampling. Simple random sampling may again be of 2 main types. Simple random sampling with replacement and simple random sampling without replacement. So what is simple random sampling with replacement? When each member or unit of the population is selected one by one into the sample and the unit selected is being returned to the population in such a way that at each draw, each member of the population will get the equal probability of being selected. Let us try to understand this concept. So there are some members in the population. Suppose there are some balls in an urn. We select a ball at random. We note down its color, if I am interested in the color, and return that ball into the urn. That means I am not keeping the ball outside. I am returning the ball into the urn. So what will be the composition of the urn after the first drawing? It will remain as it is because I have returned the ball into the urn. Then I'll draw a second ball. I'll note down its color and then return it to the urn. So you see, if initially I started with n number of balls in the urn, I'll retain n number of balls in the urn after each drawing. So that also leads to the fact that I can draw the same ball more than once in my sample. We keep this in mind because when we will study the next one, then we can appreciate this fact. Also, you see, whenever we are making any draw in case of SRSWR, there are always capital N balls in the urn, and since we are drawing the ball at random, the probability will be 1 by n every time. The other one is simple random sampling without replacement, which is abbreviated as SRSWOR. Here also, from the population, we'll draw members 1 by 1, and after each drawing, we will not return the individual into the population. We'll keep the individual aside. But we'll not return that individual in such a way that at any draw, each of the remaining members of the population will get the same probability of being selected. Let us try to understand this more critically. Let us go back to our ball drawing experiment from the urn. So we have a number of balls in an urn. Let there be small n balls in an urn. I draw a ball at random. I note down its color, but I do not return it to the urn. I keep it aside. So if I start with n number of balls, after the first drawing, what will be the number of balls in the urn? N minus 1, definitely, because I have not returned the first ball into the urn. Now I draw another ball, second ball. Again, I note down its color and keep it aside. That is, do not return it to the urn. So after the second drawing, you see the number of balls will be n minus 2. That means with each drawing, the composition of the urn gets changed. So this is SRSWOR. The composition gets changed, mind you. But in the first case, the composition does not get changed in case of SRSWR. And you see, when we talk of the probability of the remaining members of being included in the sample, in case of SRSWOR, what is the probability that any member will appear? 1 by capital N because we start with n number of individuals. In the second drawing, it will be what? 1 by n minus 1 for every other remaining individuals. While we will be making the third draw, since we have already kept 2 individuals or objects aside, there are n minus 2 individuals. So when we are making the third draw, the probability will be 1 by n minus 2 and so on. Now we talk of a parameter and a statistic. What is a parameter? Any statistical measure based on population values is called a parameter. So population mean, population variance, etc. are parameters. Now why do we study this definition? You see, suppose my objective is to find out the average height of an adult Indian. So actually what we have to do, we have to go to each and every adult Indian, we have to measure their height and then sum them up and divide by the total adult Indian population. This will be a very huge task if we want to enumerate the whole population. So that is why I said in almost all statistical analysis, we do not enumerate the whole population, we enumerate the sample. So we take a sample from it, right? But what is my intention? My intention is to measure the adult Indian average height. So what is that? According to this definition, it is a parameter. So like population mean is a parameter, population standard deviation, population proportion, etc. may also be parameters. Now we come to a statistic. A statistical measure based on sample values is called a statistic. That means, as I mentioned earlier, from the population we will take a sample. Now if I want to measure the population mean, I might use sample mean to get a likely value or to guess the population mean. This likely value or the quantity with which I guess the population parameter is called a statistic. So in our situation, sample mean will be a statistic, right? So any statistical measure based on sample values will be called a statistic. A statistic may be a sample mean, sample variance or sample standard deviation, sample proportion, so on and so forth. Now see, for a given population, a parameter must have a fixed value. Like population mean, it must be fixed for a given population. But will a statistic remain fixed from one sample to another? Not necessarily. Suppose there are 2000 individuals in a population and suppose I am interested in height and my resource permits me to draw a sample of size 10, that is 10 individuals will be selected by me. I select 10 individuals randomly and measure their height. So sample mean I have calculated. Now do you think if I do the sampling operation once more, that is I take 10 individuals again from the population, shall I get the same individuals? Not necessarily. I will not, in most probable way, I will not get the same 10 individuals. So what will happen? The sample mean will change. So for these two samples, the sample mean will change. So that means, in general, the value of a statistic may vary from one sample to another. This variation in the value of a statistic is known as its sampling fluctuation. Now see, statistic itself is a random variable. Why? Because the individuals have been selected randomly. So whatever value we have computed on the basis of those individuals will be random variables. And what is a statistic? A statistical measure based on these sample values. So that means a statistical measure based on some random variables, basically more precisely a function of these random variables. So a statistic will itself be a random variable. Fine. So a random variable will have a probability distribution. So similarly, a statistic will have a probability distribution. This probability distribution in the value of a statistic is known as its sampling distribution. And in this course of study, we are interested in sampling distributions. We have studied simple random sampling with replacement, simple random sampling without replacement. Now, in any real life situation, can you say how we can actually draw a random sample from a given population? So we were discussing the procedure for drawing a random sample. So first what we have to do, if there are capital N individuals in the population, we have to serially number them from 1 to n. Then we have to use random numbers. There is a table called random sampling number table. So we have to go on reading random numbers. Now depending on the random number, we will choose the population units bearing the serial numbers. So we will choose them. We'll go on choosing them until the sample size that we intend to is met. Now in case of SRSWR, the same member can be selected again, while in case of SRSWOR, we cannot select the same member. That means if the same member or the same population unit with the serial number comes up, we will reject that population unit for the subsequent drawings. So this is how we will select in practice a random sample, both SRSWR and SRSWOR. The question arises, what are the differences between SRSWR and SRSWOR? Obviously, one difference we can understand that in case of SRSWR, the same member can reappear in the sample, while in case of SRSWOR, the same member cannot reappear more than once. So this is the basic difference, but there are more subtle differences of SRSWR and SRSWOR. Like you see, in SRSWR, in an extreme case, it is possible that we select only one population member in all the drawing. That is theoretically possible. In SRSWOR, that is never possible. That means in SRSWOR, we are guaranteed to get more elaborate information than SRSWR. So we can say that SRSWOR will cover more of the population than SRSWR, and it can be shown that the error committed, the sampling error will come a bit later to it, but the sampling error committed in case of SRSWOR will be less than that of SRSWR. So in general, we can say that SRSWOR is a more efficient sampling scheme than SRSWR. Now the question of sampling error arises. What do you mean by sampling error? Fine. Let us go back to our example of average height. I want to find the average height of an adult Indian. Now I take a sample. Fine. Now, do you think the sample mean that we will get will be exactly equal to the population mean? Not necessarily. So the sample mean may get deviated from the population mean. That is quite possible. So this deviation is the error. Now, am I responsible for this error? No. Whatever sample I have selected the sample randomly, whatever sample I have got, I have taken the sample mean. So that means this error is not committed by the sampler or the enumerator, but this error is an intrinsic property of sampling. So this is called sampling error. Now how to measure the sampling error? The sampling error can be measured in terms of mean square error or the sampling variance or even sampling standard deviation sometimes. Now in case of SRSWR, this sampling error is more than SRSWOR. So that is why we say that SRSWOR is a better sampling scheme. But do we commit only sampling errors? Is there no role to play by the enumerator or the investigator or the sampler? Yes, those are known as non-sampling errors. So non-sampling errors are something which are committed in the process of conducting the sampling operation. Like, suppose the points are in decimals. Suppose the figures are in decimals. So I might place the decimal point wrongly. That is one kind of error. This has nothing to do with the sampling. Sometimes it is possible that I record the data wrongly. So that is also an error of my part. That has nothing to do with the sampling. And it is seen that when we investigate about, say, age, most people are likely to state their ages in multiples of 5. Suppose a person is of age 83. It is more commonly observed that either he will say that my age is 80 or my age is 85. Very seldom he will say that my age is 83. So that means there will be an error while recording the age of that person. So that is also non-sampling error. Also, sometimes income figures are required. For many economic survey, income figures are required. Now, very often, the income figures are not stated properly. That means either we get a lower income figure or we get a higher income figure. So these type of errors occur. They have nothing to do with the sampling. So these are not sampling errors. These are called non-sampling errors. So the main sources of non-sampling errors are something like this. lack of proper specification of the domain of study. Suppose I want to conduct study on middle class families. Now, what do we mean by middle class families? To me, middle class families may be those whose income range is from A to B, and for somebody else it may be from A dash to B dash. So that means there may be lack of specification on the domain of the study. Incomplete coverage of the population or the sample. I may not cover the whole population unless I know the full list of the population members. I cannot draw a random sample faithfully. So that means there is also a possibility of error. Faulty definition. Faulty definition. Definition of poverty line. We have to be updated about the definition of poverty line. It gets changed from time to time depending on the policy of the government. So these definitions are to be crystal cleared. Defective methods of data collection. Sometimes we do not collect data at all randomly. We go to an individual, collect data and ask that individual who are his known persons. Then we collect data from those known persons, which are easier to collect. But this is not random sampling. So this is a faulty method of collecting the data. And finally, when we tabulate the data, a lot of error occurs. So one thing is to be kept in mind before doing any kind of statistical analysis. We have to scrutinize the data properly. In the next topic, we will come to chi-square distribution. We have already studied standard normal distributions. Can you imagine what is our standard normal distribution? So if you can recall, a standard normal distribution is a normal distribution with mean 0 and variance 1 or standard deviation 1. That means if X follows a normal mu sigma square distribution, a standard normal variate Z will be X minus mu by sigma. Now suppose we have n standard normal variates Z1, Z2, Zn. A chi-square distribution or a chi-square statistic is sum of the squares of these n standard normal variates. Now mind you, these standard normal variates are to be independent. In case of SRSWR and SRSWOR, if I go back, when the sampling will be independent? Let me first take SRSWOR. I select a person at random. I note down, say his or her height, and then I keeping aside. I do not return him back to the population. That means whichever individual I have drawn, that influences my further drawing, because that individual will not be a member of the population anymore. So that means here the drawings are dependent. That means whom I am drawing will influence the further drawings and so on. In case of SRSWOR, I select a person at random, I note down his or her height, and I return him or her back to the population. Now do you think the next drawing will depend on the previous drawing? Obviously no, because the population composition remains as it is. So in this situation, the drawings will be independent. And if the conditions of the drawings, conditions of the sampling remains unaltered, in that situation, the drawings will be identical as well. That means the random variables, those will be generated, will be identical and independent. So in particular, if Z1, Z2, Zn be n standard normal variates, the chi-square statistic will be defined as, this symbol is called chi-square, what you can see on the screen, chi-square. It is Z1 square, Z plus Z2 square plus Zn square. Chi-square is said to have a chi-square distribution with n degrees of freedom. You see there are n standard normal variates, sum of squares of n standard normal variates, and that is why it is n degrees of freedom. Now, in a very short manner, I will just try to give you an idea about degrees of freedom, because it is a very advanced statistical concept which is out of the scope of our course of study right now. But in a very nutshell, I will try to describe what do you mean by degrees of freedom. Indicate what do you mean by a degrees of freedom. Suppose you are given three quantities A, B and C. I ask you to choose these three quantities according to your wish. So you can choose A according to your wish. You can choose B whatever you feel like. You can choose C in a similar fashion. So that means as if you have a freedom of degree 3 to choose the three quantities A, B and C. Now I ask you to choose A, B and C such that A plus B plus C is equal to say 10. Now see, you will be able to choose any two of them. You choose A and B, C will automatically be determined. You choose A and C, B will be determined. Similarly, you choose B and C, A will be determined. That means you don't have that much freedom to choose A, B and C as earlier. So this is some sort of an idea of degrees of freedom. The PDF of a chi-square distribution with n degrees of freedom is given. It's not a very simple PDF, it's a bit complex PDF. It's given on your screen. You can see 1 by 2 to the power n by 2. Then this is called a gamma function. Gamma n by 2, then e to the power minus chi square by 2 into chi square to the power n by 2 minus 1. And here chi square lies between 0 and infinity, which is very obvious because tangent normal variates lie between minus infinity to infinity. So the square of them will lie between 0 and infinity. So definitely, since chi square is the sum of squares of these, so chi square will lie also between 0 and infinity. There are some important properties of chi-square distribution. The expectation of the mean is n, that means same as the degrees of freedom. The variance is twice n, that is twice the degrees of freedom. You have to remember these two. And the distribution is a positively skewed distribution. We can see the graph in the next slide. See the graph of a chi-square distribution. Its longer tail is towards the positive direction of the x-axis. So it's a positively skewed distribution. I just recall the fact that when the longer tail is towards the positive direction of x-axis, the distribution is positively skewed. When the longer tail is towards a negative direction, it is a negatively skewed distribution. And when the two tails are more or less equal over the two sides, then it's a symmetric distribution. So clearly, chi-square distribution is a positively skewed distribution. And one more thing I'd like to point out in this diagram is this. If you can see a shaded area, this is nothing but the probability that the random variable x is greater than that value. This is called the tail area. So this is more or less all about chi-square distribution. This chi-square distribution is needed for hypothesis testing, estimation, interval estimation, so on and so forth. We will study those in our next courses of study. So this chi-square distribution, you have to remember the properties of the chi-square distribution, and the shape is very important for the chi-square distribution, which will lead us to T, F, etc. distributions in future. Thank you.